which explains about different echoes from the we have studied. So I think it's a little bit advanced chapter, but this chapter will be helpful to understand the some imaging technique, how MRI signal comes from the imaging process sequence. So first, I would like to explain about the Han echo. In previous lecture, I already explained about gradient echo and this spin echo. Gradient echo is generated by the compensation gradient field, and the spin echo comes from the 90-degree RF pulse, the combination of 90-degree RF pulse and the 180 RF pulses. Even though we use the double 90-degree RF pulses, the spin echo also comes from this combination of RF pulse. Where is the pulse? Here. Okay. Okay, it works. Yeah, thank you. The echo RF. This is the a kind of RF echo which comes from the two double 90-degree RF pulses. So the difference between this echo and the spin echo is that this echo do not use the 180 RF pulses. So we call this echo as Han echo. Han is the name of a famous person who studied about the famous Han echo in MRI field. So how come this echo comes from? First, when 90-degree RF pulse is applied, then transverse magnetization generated. So just after that, the spins are defaced due to the field spin interaction and field in homogeneity. So some times lapsed, the spins are defaced out. So transverse component becomes seriously reduced at this time. So this figure is corresponds to the just before the second 90-degree RF pulses. So just after the second 90-degree RF pulses, all spins are flipped along the 90-degree RF pulses axis. So here we assume that the RF pulses are applied along the x prime axis. So all spins are flipped. Here, the white color arrow means that the fast rotating spins, but the black colored arrow means that the slow rotating spins. So that means the upper spins, as explained here, the second 90-degree flips, the faster spin is up here, but the second 90-degree flips the slow spins down here. So the white arrows comes up, but the black arrows comes down here. After that, all spins are continuously precessed along the main magnetic field parallel to G-axis. So these spins precess in this direction, and these spins precess in this direction. Also, the black spins also precess in this direction and in this direction. So after that, Yeah. These spins are white arrows, and these spins are black arrows. So all spins are precessed in into the minus y prime axis here. So all spins are rotate to the y prime axis, but the spins are focused in the shape of umbrella like this. But the transverse component becomes increasing. So that's why the echo is generated here. So as shown here, the maximum signal is not equal to the spin echo, because the spin echo is generated by all spins are in parallel direction or in phase state. But in Han echo, signal does not generated by the in phase state. All spins has some dispersion state. So the Han echo signal, the magnitude of Han echo signal becomes the half of a spin echo signal intensity. So that's the characteristics of Han echo. So this Han echo says that the echo also generated by the 90 degree to 90 degree RF pulses. So from this theory, we can infer that the arbitrary combination of RF pulses can generate echo signal. Okay, so in special case, when the two combination of 90 degree RF pulses generated Han echo. This slide shows another different RF echoes. Using the using the combination of three 90 degree RF pulses, a kind of RF echo is also generated here. So this spin diagram shows the just after the second 90 degree RF pulses, as shown in the Han echo spin diagram. So after that, all spins are refocused like this, as same as Han echoes. After the dephasing the spins during the time interval Tm here, defined here, the other 90 degree RF pulses are applied. So after that, the spins are, after the third 90 degree RF pulses, the spins are focused like this, because also these spins are also the shape of an umbrella here. The fastest slow spins here, and the faster spins are here. So this slide also shows that the stimulated echo signal intensity is also a half of spin echo signal intensity. Here we defined the echo time in different manner with the spin echo signal. In spin echo signal, echo time is defined as the time interval between first 90 degree RF pulse and the peak of spin echo signal. But in stimulated, we call this echo signal as a stimulated echo, which comes from the combination of 3 90-degree RF pulses. So I explained about the Han echo comes from the combination of a double 90-degree RF pulse. So if we use the combination of 3 90-degree RF pulses, then we can get the stimulated echo. And for the stimulated echo, the echo time is defined as the time interval between first 90-degree RF pulse and the spin echo minus the time interval between second RF pulse and the third RF pulses. So here the time interval between first and the second RF pulse is half of echo time, and the time interval between third 90-degree RF pulse and the spin echo peak is the half of echo time. So the time interval between first 90-degree RF pulse and the echo peak is defined as echo time plus Tm. Tm is the abbreviation of time of magnetization. So we usually call this time as Tm. So this time definition is somewhat different from echo time of a spin echo sequence. Okay. So this sequence is usually used for the localization of a spectroscopic technique. Okay. From this theory, we can generate the several echoes simultaneously using the combination of 3 RF pulses. Here, 3 RF pulses are used here, here, and here. Then, in general, these RF pulses has a Philip angle of alpha. Okay. So it's a general RF pulses. Okay. Then the 5 echoes are generated from the combination of 3 RF pulses here. So the below figures explained how come these echoes are generated. So first echoes are generated by previous 2 RF pulses. So it's just Han echo, as explained before. When we use the 2 90-degree RF pulses, then the Han echo is generated. But in this figure shows that even though we do not use the 90-degree RF pulse, just the Philip angle of alpha, then the echo is generated here, and the timing is the same as the spin echo. So the time interval between first and the second RF pulse is equal to the time interval between the second and echo peak. So now this echo is called as a primary echo. So these echoes are dephased due to the T2 star decay after the primary echo, but the dephased spins are refocused by the second RF pulse here. So the secondary echo from the primary echoes are generated with the time interval B. So B time interval is equal between this time. So we call this as a secondary echo of these primary echoes. After that, the combination of 3 RF pulses also generated a stimulated echo. Even though the Philip angle of these RF pulses are not 90 degree, the stimulated three combination of RF pulses generate the stimulated echo. The principle of stimulated echo here is the same as the before. And the second and the third RF pulse also generated a different primary echo here. So this is the first, second, third, and the fourth echo here. So the first echo comes from the combination of second and third RF pulses. And also, the first and the third RF pulse generates the primary echo with the same time, same principle of echo time here. So the combination of three RF pulses generates the 5 echoes here. So the multiple echo generated multiple RF pulses generated multiple echoes. So it's very complex when the RF pulses are repeat with a short time interval.
Excuse me.
Yeah.
Yes, I'm not confused. I want to know about first we can say the primary echo is the signal, right? This is the image, the result.
Yeah, the
result
echo,
of the primary echo.
Yeah.
And then the second is inverse the result of the first. Or not. First, second is like an inverse.
Inverse, it depends on the phase of RF pulses.
So we can say this is the first, this is the second, third, the fourth. It is the third and the fourth is what is the difference between them? For I mean the results or something.
You mean
the result of the each step?
Each step?
Yeah. What are difference?
The result?
Yeah, the results.
The result is the difference of two echoes are the T2 star decay is different, and each echo comes from the different combination of RF pulse. The first primary echo comes from the second and the third RF pulse, and the fifth primary echo is generated by the combination of first and third RF echoes. So the echo time is different. Okay.
So and can I say that, for example, the result of the process, the fifth step is better quality than the other, or
no,
I cannot say.
It's the echo time is very long, so the image quality.
Yeah, image quality. I want to know about it.
Is depends on the echo time, okay, and the echo time is affect the T2 star decay. So the image contrast is different for each echoes because the echo time is different. So we cannot say that which echo generates the best image. It depends on the contrast of tissues. Some tissue has good contrast for one echoes, then the other echo has generates the lower contrast for specific tissues. So it depends on the T2 or T2 star value of tissues. Okay.
Can I ask?
Yeah.
The original signal is the sorry. The original signal is this one first, second, and third. This is the original.
Original?
Oh.
What do you mean the original?
Because
Alpha, right?
this one is the result
Alpha
from
cross.
Equal.
this one and this one,
Yeah, right?
and this is the equals.
You said right.
Yeah, the RF pulse is indicated by red arrows below.
This is the
Yeah,
RF.
those are
pulse.
RF pulses.
So this one is the echoes
Yeah,
that
echo.
result from the two of the
RF
RF
pulses,
pulse.
right?
And then okay, this one.
Mhm.
So this is the step
Mhm.
that that has results. This one
Mhm.
is it
Yeah,
right?
yeah, yeah.
Right.
So first the two of the RF pulse
Mhm.
can I say generated the echo,
Yeah, primary echo.
primary echo,
Yeah.
and then the primary echo and the third
Third RF pulse.
RF pulse
Mm.
resulted secondary echo. This
Secondary echo,
one.
right?
And this one or this one?
The next, the small,
Small one.
Inverse.
Small
Yeah,
one.
small one. Because the timing of echo is depends on the timing before the RF pulse and the primary echoes. So we know that the secondary echo or this echo comes from the RF pulses and primary echoes because the timing of P and P is equal here. So this echo is not considered as the echo of primary echo because the timing is not consistent, same as the B. Okay, so we said that this echo is the secondary echo of the primary echo because the timing is the same as a B. Okay. And this echo comes from the stimulated echo by the combination of three RF pulses because the timing of between the first and the second RF pulse is A, and the time interval between the third and this echo peak is A. So we infer that this echo is a stimulated echo, comes from the three RF pulses.
So when the echoes happen, it should be the time is equal. The time is same because I saw A.
Yeah.
When primary echoes happen, the timing A is
Yeah.
same, and
Yeah.
then when the secondary echoes happen, B and the timing
B
also
and
the same.
P. Yeah.
Is
So
it
yeah,
the requirements?
we determined the echo using from the timing between the echoes and the RF pulses. So we can infer this echo as a second echo because the timing interval P and P is equal. Okay, so this stimulated echo is defined as a stimulated echo because the timing interval A and A is equal. Okay. Yeah.
Just one question.
Yeah.
What if the two times A and B are equal? Is the only effect that
I will explain next slide.
Oh.
Okay. Here, in general, the combination of three RF pulses generates the five echoes as explained in previous slide. But in this case, the time interval A and P is not equal. But when time A equal B, the case is depicted in this figure. So at that time, this A, since the A is equal to B, the echoes are overlapped here. Okay, so the positive echo and the negative echo is cancelled each other. So the small echoes are generated here. So this overlapped echo means that in imaging, if we use the this echo for the imaging reconstruction, then imaging has some artifact. So some signals are cancelled out. So some areas becomes dark. So this is a serious problem for MRI imaging. So when a process sequence is designed, these echoes should be considered, whether some echoes are overlapped or some echoes are interfering each other. Okay. In general case, the RF pulses are applied repeatedly in the same intervals. So, from this slide, all echoes are overlapped each other, and we can infer that slice comes from the each RF pulses. So from the first RF echo, only FID signals are generated, right? And from the second RF, only FID signal is generated from the second RF pulses. But from the third RF pulses, the primary echoes are generated, or Han echo is generated from the first and the second RF pulses here. But just after the third RF pulses, in the right side of third RF pulses, the FID signal comes from the third RF pulse, and the spin echo, Han echo signal is overlapped here. So just before the third RF pulses, only a Han echo signal is generated. But on the right side of third RF pulses, the FID signal and Han echo signal is overlapped. From the combination of three RF pulses, the stimulated echo is also generated, as shown here, right? So at this time, the stimulated echo and Han echo, this Han echo is generated by second and third RF pulses, and but for the on the right side of third RF pulse, fourth RF pulse, the FID, Han echo, stimulated echoes are overlapped here. So after that, all Han echo, stimulated echo, and FID is overlapped here in the same manner. So after several RF pulses, several echoes and FID signals are combined in the each signals here. So it's very complex signals are generated.
So they can get it back. They can extract.
No, we cannot extract each other. So we have to use the property of each signals. So we have to control the timing of each RF pulses, and sometimes we use the overlapped signal for the imaging sequence. So after several RF pulses, these signals becomes steady state. So we call this signal as steady state free precession. So the abbreviation of steady state free precession is SSFP. So usually this condition is occurred when the TR, time interval between the RF pulses, is shorter than T2 or T1. relaxation time, because the second RF stimulated echo or spin echo is not enough, is not decayed enough during the time interval TR. So for long TR, all spin echo or stimulated echo becomes almost zero due to the relaxation T2 star relaxation time. So in this case, TR is shorter than T2 star. Okay. So this problem comes when the TR is very short compared to the T2 relaxation time of tissues. And I would like to explain about the partial flip angle. What is the partial flip angle? In strictly, partial flip angle is partial flip angle equals to low flip angle. So when we use the large flip angle, for example 90-degree RF pulses, then we can get the maximum signal when TL is relatively long compared to the T1 relaxation time, because the almost magnetization recovers to the equilibrium state, then the next signal is maximum when the flip angle is 90 degree, as I explained before. But in the case of short TR compared to the relaxation time, that means the next RF pulse, when the RF pulse is applied, the longitudinal magnetization is not equilibrium. So the longitudinal magnetization is determined by the T1 relaxation time during the TR repetition time. So the next transverse component strength is determined by the longitudinal magnetization. So the MR signal is proportional to the longitudinal magnetization product by sine flip angle. Okay, so this longitudinal magnetization, here the superscript minus means the longitudinal magnetization just before the RF pulse. Okay, plus means just after the RF pulse. So the transverse component just before the RF pulse is 0, right? But after the 90 RF pulses, the transverse component is determined by the longitudinal magnetization strength just before the RF pulse, produced by sine alpha, where the alpha is the flip angle. Okay. So this is an example of signal strength when the flip angle is 90 degree and the longitudinal magnetization just before the RF pulse is M0. M0 means the equilibrium magnetization. So this means that the RF pulse is the first initial RF pulse. So just after the longitudinal magnetization, just after the RF pulse, of which flip angle is 30 degree, then the longitudinal magnetization becomes M0 product by cosine 30 degrees. So just about 87% of equilibrium magnetization. So this figure shows when alpha is 90 degree, then this magnetization, longitudinal magnetization is the about 87% of this diagonal vectors. Okay, and the transverse magnetization is M0 product by sine 30 degrees. So about half of equilibrium magnetization.
Excuse me, sir,
Yeah.
for the value of M0.
M0 here.
Normally, how can we get this value? We
M0 is
equivalent magnetization.
equilibrium magnetization, or the net magnetization is the vector sum of individual nuclear magnetism.
This is already fixed.
Yeah, this is already fixed for the tissues.
For the tissue, like for example, how can I say the name of the sun? For example,
It depends on
this
the
machine.
magnetic field and spin density, and sensitivity of RF coil and temperature.
So that means the machines machine already fixed the M.
Yeah, M0 is
value.
already constant values for imaging condition. Okay. So M0 depends on the magnetic field, RF sensitivity, and the voxel size, and the tissues, and sensitivity RF coil, and amplifier gain, and so on. So it depends on the tissue, hardware, and the environment. Okay. So this is called as apparent spin density. Okay. Oops. Yeah. When the RF pulse is